All right. Good afternoon, everybody. Just to those of you who have already joined us, I think we're gonna wait a couple of minutes to see who shows up, but welcome, and we look forward to this presentation by Professor Sain. All right, why don't we get started? My name is Marcus Bussman. I'm the chair and a professor in the Department of Mechanical and Industrial Engineering here at the U of T, and I want to extend a warm welcome to all of you who have joined us for the last research spotlight seminar of 2021. For those of you who are alumni who may not be on the university, I just want to say that we're approaching the end of a fall term here at the university and here at U of T Engineering, where for the most part we've been very fortunate to return to on-campus and in-person teaching of our students, both undergrad and grad. And it's the university has done a lot of things right, I think, in terms of keeping COVID under control on campus. I mean, people here on campus are mandated to be vaccinated. There's a lot of protocols in place to keep people safe. And I think, my understanding is that the university really has had very few issues the past few months as we've brought people back on campus in terms of COVID. And so I think we consider ourselves very fortunate. And I think the plan is for the university as a whole to do even more in-person education in the coming months, kind of in response, in part, to the success that engineering has had these past 4 months in getting that done. So it's a real privilege now to introduce our speaker for today. I just want to say a few words, and then I'm going to let him have at it. So Professor Mohini Sain is a world-renowned researcher in his field. Joined the university, I think, about a little more than 20 years ago, I think in '99 or so. He is by training a chemist and a chemical engineer, and joined the university at first into its its faculty of forestry, and was in the faculty of forestry for most of 20 years until 2018. He served as dean for 5 years. But in 2018, the university made the decision to move the faculty of forestry, a large part of it, into the Daniels Faculty of Architecture. And Professor Sain took the opportunity as an engineer to request to come into our Faculty of Engineering and asked to come into MIE. And so Mohini has been a part of mechanical and industrial the past 3 years, and is really one of our foremost scholars and educators. So Mohini is world famous for the work he has done on what he will describe in a few minutes, but on biocomposites and on biomaterials and the use of biomaterials in various processes and for creating various materials. He has done amazing things over 20 years. He's published many hundreds of papers. He has many patents to his name. He has a huge research group. He has brought in many millions of dollars in research funding to the university for his work. He has won many awards. Most recently, a few months ago, he was named a Fellow of the Royal Society of Canada. And in coming over to MIE, and in large part because of his own relationship with the Ford Motor Company in Windsor, he brought an endowed chair into our department and is the initial endowed chair, Ford chair, in sustainable materials in the Department of Mechanical and Industrial Engineering. Really, I could, Mohini's CV is long, his list of awards, his list of accomplishments is very long, but I think it's we in MIE are absolutely delighted that a few years ago he chose to come and join us. And it's now a privilege to introduce him to you and allow him to tell you a little bit of the work that he has done and I think will continue to do around the topic of renewable materials. So, Professor Sain.
Thank you, Marcus, for your humble words. And I also want to welcome all of you. And thanks for giving me opportunity from the department to summarize some of the work I have done during my past career. And also I'd like to put some perspective of what is currently going on and where the future of my research going to get through. So the topic itself is sort of a recent indication what's going on in the world. It's a transformation happening in the world in terms of energy, but that energy doesn't necessarily relates to energy for processing or even for transportations and other utilization. Energy, in fact, translates into various domains and various themes. So today I will cover, to start with, a clarity of circularity of the material, which has become the core research area for the last 20 years or so in my group. So what it means that we always are in the forefront of material discovery. If you look at in the overall global sense, since probably early 1990s, and since that time, it has gone through several ages. And if you look at these particular slides, it gives you an idea how the progress has been made in the materials area from the copper, bronze, iron, elastomers, polymer, composite, and then to functional materials, more lately molecular materials, and then low carbon materials, which are very, very recent. So if you take the transition happens, and each of these transition leads to a significant amount of growth and innovations in order for us to move to the next forms of the materials world. So when you have done a lot of good work, at the same time, as a scientist, I sometimes feel that we also made some real mess to this universe and to the Mother Earth. And in 1980s, actually, when I was a young engineer, and I've been given a task to design some cable for electrical installations, and asked to do so by not to using a lot of these materials, which are so-called iconic material at that time, elastomers and plastics and composites. The idea at that time was how you can introduce the natural materials and bring more renewable carbon so that you can reduce the footprint. And that I'm talking about the early 80s, 85. Since then, it has been progressed, and I will give you a summary how that things are evolving and what it's really shaped in today. So we are talking about today's circular economy, not really an economy. So from 1920 and to 2000, I would say we were in the linear economy era, where we are extracting raw materials, we are processing them with a high energy intensive process, then trying to functionalize them again, not considering the effect on Mother Earth or on climate change. And then products goes into that becomes a product. Products goes to the manufacturing and final use. And then also, as a scientist, we did not consider, what happens in the end of life period. So therefore, the whole system of management of material was not really well articulated in those early era for 50 or 60 decades, where the really revolution happens in the material world. Now in late 20s of the 21st century, we started thinking about this, and because primarily of the climate change and climate change mitigation effect. And now we are in a new era where we are designing a concept of circular economy, and correspondingly, we are also designing a circular materials economy, which means that any material today we make, right from the inception to its end of life, we need to think through carefully so that it can sustain, it can reuse, and it can be recycled or biodegradable. So embodied carbon actually remain as a minimum footprint. So this is where I think we are going. So my next few minutes, I will concentrate on how that happened over the years in the research area where I have done in the past, I think 35 years. So let me give you an example what happened in early 90s when I was working with Professor Ray Woodham and John Bartines from forestry. I was in partnership with USDA at that time, and the whole concept of this material transformation came at that point of time, where we have been looking at different ways to introduce materials coming from the natural resources containing forest resource, agricultural resource, and how that can reduce the use of fossil fuel plastics and chemicals in the process. And as a matter of those partnership, between USDA, we conceptualized 1989, and when I was not actually here at EFT, but you are outside EFT, with the cooperation of the EFT, we successfully started a global consciousness on the wood plastic composites, so-called industrial forum. I think that the whole platform was how we can take these fundamental ideas of our research, where you can introduce bio-based material to replace some of the plastics or other artificial materials, and then introduce into their product. So that concept came Sain under the leadership of the University of Toronto. It was probably not very well known. That's why I just wanted to give you a bench. But this is our legacy project. Actually, that project has been spearheaded by the University of Toronto. And we, in 1994, with a fellow from chemical engineering, his name is Dero Swanda, we started the first company in Canada where we demonstrated that we can introduce material and we can make this material stiff, structural, performant, so that it can be used for decking and building applications. So that was the concept. So that concept became actually rapidly growing. And in 2008, the process became so expensive that it took up about $7 to $8 billion business at that point of time, including China has been growing rapidly. So this gives us a lot of confidence in terms of taking a concept from the laboratory and put in a successful order. And now we think, based on that particular success story, particularly our team at University of Toronto keep on moving in that direction, and then we put in a different platform and come up with their fundamental knowledge bearing to the value-added applications. Our next step was, on which we thought we are basing on, is the fundamental breakthrough in the critical thinking. So if you have really a critical way of your thinking in such a way that you can create innovation, that innovation, if you can follow through to the fundamental process, and process means a scientific and engineering process, it might lead to, at some point of time, sort of an engineering problem. And that engineering problem could lead to ultimately engineering fundamental principles, adaptation, and lead to a commercialization. So we followed that principle. And here I give you an example. What we did, we said that, well, if you have a material is usually composed of macro, nano, micro, atomic level materials. Now, what happens if we can go from a macro level to atomic level, and how fast we can go, how effectively we can go with a minimum energy requirement? So that concept has been introduced in a patent early in 2005 by our group, where we said that if you want to have an atomic scale, in the molecular atomic scale material, the one way you can do that is, instead of having a lot of chemicals and energy to put in, you can look at the state of physics of that material and then backtrack yourself in the thermodynamics and the kinetic part of the material and come up with a new solution. And this is exactly what happened. I'll give you an example. Someone told me, well, Mohini, you are in the pulp and paper industry. Pulp and paper industry made a lot of pollutions, but it doesn't work. So the concept that time we introduced, if we really have to make a tiny materials from a very robust composite natural product like tree, then we have to find out what actually we can do in terms of changing the fundamental and physical parameters intrinsic to the composite material. We quickly figured out one thing, that if it is a biomaterial, essentially is susceptible to water. And if it is absorbing water, then there might be a way to freeze that water. And the reason we thought that if we freeze the water, there is a volume expansion at certain temperature. And if that volume expansion happens, there will be internal pressure. And if internal pressure happens, that we can then use that internal pressure to deprive it, or we said open the whole material chain from the macro level to the molecular, to the atomic level. And this is the concept we introduced. Here we say abnormal volume expansion of water to ice crystal leading to internal pressure and low energy defibrillation. So this is the concept we introduced early in 2005. We patented the process. And then based on the core process fundamentals, we started working on how that can be probably demonstrated in the larger scale. What we did, the exceptionally low temperature and a dynamic mixing mechanism will lead to super thermal exchanges. So what we did, we found that if we can develop this ice crystal in any biomaterial, and by freezing the water, and then we dynamically shear it, shear actually gives a lot of heat. One of the challenges of keeping the biomaterial in a more thermodynamically stable form, or even kinetically stable form, is to manage the heat. And the thermal management, one of the major issues in this type of material. So what we did, we tried to deepen a temperature of minus 80 degrees Celsius. And as we go deeper and deeper in the super low temperature, the thermal exchange become hyperactive. And as a result, we got exceptionally good quality molecular level material at a significant amount of low energy level, and at the same time, at a very quick kinetic level. So this fundamental idea led to few important things. And I will just quickly show the video, because this video has been run at that time. Hopefully I can do that. You can give you the idea what I did.
Right? It's in pretty high gear these days, but there are limits. You wouldn't say use your vegetable scraps to build a new car, would you? Or would you? Maybe that's not so far-fetched after all.
Field of wheat, cars on a highway. At first glance, they don't have much in common, but that might not be the case for long. Mohini Sain heads up the Ontario Biocar initiative.
This is a gel, like jello.
He's dreaming up ways of turning straw, corn cobs, wood chips, pretty much anything into car parts. The car of the future might not be made entirely of straw, but even using a small amount will help.
So what happens in the Biocar? If you use these fibers in a plastic material and increase the property 2 times, then you can reduce the weight of the car by 30–40%. That's what the catch of why it is so important for the car industry. It will make the car lighter, and at the same time, if you make the car lighter, it will save energy because it will consume less gas.
To transform straw into a car, Sain's team grinds up bio-waste and coaxes 3 kinds of fiber out of it. There's cellulose fiber, that can replace a fiberglass car seat. Polysaccharide, basically starch, ends up as plastic, the foam in the seat or a heads-up GPS in a windshield. And there's lignin, raw material for carbon fiber. Transform wood fiber into biomaterial, Sain and his team use fungus to break it down. Fungi from diseased trees gets cooked up in the fermenter until it releases its enzymes. It's like a high-tech brewery.
At the
this fermenters is used for growing up the fungi, or growing the fungi to produce the enzyme. So it's exactly what you would use to make beer, except it's a very expensive piece of machinery. At home, you use a stripped down version of this.
The goal is to isolate specific enzymes that will modify the fibers and make them behave in just the right ways. Each of the different materials then gets specialized treatment. When the enzymes are done with the cellulose fiber, it comes out looking like rabbit food pellets. They can be used straight up to make a fiberglass or plastic substitute. Clear pellets behave like petroleum-based plastics. They can go through the ringer. These big extruders squeeze out sheets of bioplastic ready to cut and vacuum form into shape. Or Sain combines the nanofibers with clay and fashions them into a molded car seat or a running board.
Can be done with that injection machine.
The modified starch gets a different treatment.
So it's not a popcorn, it's a fiber coming from wheat straw. It is being bleached. These fibers construct of millions of microfibers and nanofibers.
The mix gets tossed in this grinder, kind of like a giant food mill. Out of the bottom drips a nanofiber gel that's 99% water. Like wood pulp used to make paper, the gel is viscous enough to pass through a press and come out the other end as biofilm. Thin, flexible, and lightweight. Embed some electronics in it, apply it to a car or aircraft windshield, and it's a perfect heads-up display. Liquefied lignin, a chemical compound in plants that fills the space between cells, is squeezed into a thread and then cooked at very high temperatures. It produces carbon fiber. The carbon fiber project still needs a few more years of development, but in the meantime, there are car seats and fenders undergoing some rigorous testing. Heavy pressure in this case, extreme heat and humidity in here.
So what we try to do here, give a real-time experience to the industry that this material is real and it has a performance level which can extend, 10, 15 years down the time.
Sain is working with the government and over a dozen auto parts manufacturers to include his materials in the cars of the future. And what he can do with biomaterials isn't limited to car parts. This spray foam insulation is as effective as the synthetic ones that are in houses now, and it's almost ready for the market.
I think that the whole process of making this material from the green source is exciting, and it can be done.
So one day soon, if you tell someone you're driving a lemon, it just might be true.
All right, that gives you a sort of a video summary. I'll just go back to my next slides. I think. So, okay, so that particular concept of Biocar has been developed by Ontario Research Fund program. It was about $18 million they invested. And they told us, demonstrate as many as possible parts or engine you can make out of it. So that particular project finished by 2012. And since then, we have been continuously working with the different OEMs. And this is another example where the state of this technology, where we were really starting with a very low-hanging fruit. And this particular slide will tell you, and this is what actually a very present case in this year, this has happened. We were able to replace, a front cover of an engine which is about 500, 600 horsepower by using this kind of material. And this has been now being introduced into Ford's performance vehicle. And this is an example. Again, I'll run this, sorry. So what the technology did, it took out about 40% weight from the powertrain. Because of lighter weight, because of its functionality, and at the same time aesthetic. So as a result, the performance vehicles where a fraction of a second matters, this particular product gave us tremendous advantage to the Ford performance vehicles for the racing car industry. So therefore, you can see that when we started with very low-hanging fruit, today through the transformation of the different technology, we are able to make something which is unique and which is really transformative in nature. So that's what it shows. When you start with something tiny and then you based on your fundamentals and follow through the engineering principles and keep your goal focused to make a product to the launch in the market, it is possible, and there is a potential growth in the material for the different and diverse industry. So this was about nanoscience of renewables bioart. So when we started all these things, we also had in mind, so okay, when we can make some parts in the performance material, can we do something else? And this actually happened to us when one of these car industry came to us and said, well, we have headlights, it's pretty heavy. Is there a way we can change that? We can make some LED, which is lighter and says, okay, then we said that, well, let's see what next we can do. So we took another concept and approach out. We said, look, if we can make this material carbonious, and then we can see if it has some sort of fluorescence capability or the light emitting capability, then probably we can make a quantum dot type of material. And we say in this case, the bio dot or graphene dot material. So these few slides will give you an example how we did it and how we transform it. One of the first thing we did is reduce the energy in a different way. First thing, our concept was to decrease the temperature, defibrillate it. Now we introduce our bioengineering or biomanufacturing. In this case, we use actually a fungus which is coming from the diseased Dutcham trees, and it's in the process of expansion. It's a sort of an enzyme which goes inside the interface of the cellulose microstructure, and then it just cuts the hydrogen bond. It doesn't degrade, actually chop the cellulose molecules. Instead, what it does that it's just chop the hydrogen bond. So this particular mechanism, again, the biomechanism allowed us to further reduce the energy consumption in our defibrillation process, leading to a very high surface area and very uniform nanofiber material coming out of the process. So if this happens, we found that we can really make effortlessly these nano entities where we can use it for different applications, including making carbon out of it. And I will go to that in a little bit detail. But this process was not easy. We had to be selective. So I had to go through the microbiology, and actually I'm a chemical engineer, I'm not a microbiologist. So naturally I have to get help from the cell biology department. And with their help, we were able to actually sequence the enzyme, and we came up with a very unique protein system, which we then reverse engineered and then introduced that in our system. So we developed a biomanufacturing system where we can have this protein introduced into a biomanufacturing bioreactor and able to get this nanofiber in a very, very facile way. So that was one of the steps which we introduced. And if you can see the structure of this material, which led to 90% energy saving. If you know the pulp and paper industry, when they are trying to make some fiber, they are using hundreds of thousands of tons of gallons of energy in order to make this kind of material. So this fundamental breakthrough allow us to go to the next level. So if we can make this effortlessly, less energy, then we can burn it, in my opinion. If I can burn it, then I can make it carbon. And if I can make it carbon, I can functionalize and make other products. So few slides will give you the idea how we came up from that level to really the electronics and electrical application. This particular slides will show, once you have this material as a base, you can make a film, which is actually a nano paper. So instead of your paper, writing paper, you have a nano paper, which is tiny, and it is razor thin as your hair, but at the same time it's flexible. So therefore, we were able to make this advancement of the functional bio-nanomaterial, which has tremendous advantage in terms of its roughness, in terms of smoothness, in terms of its optical property, in terms of its electrical, thermal, and also performance property. So this gives our team a unique approach to do that. So what we discovered, that we can compete with glass. So our invention was that we can develop an organic and flexible biogas, which will compare the normal glass material. And here is the table. So if you look at this table, the right and last phase of the column is our material, which is a cellulose nanocomposites, and the second line from the right will give you the Dow Corning classical flexible glass at that time in 1969 patented process. We demonstrated that with our system, we were able to match each and every, if not exceed, some of those properties by using these natural materials. Or in other words, we were able to manufacture a product in larger scale where you have a flexible glass material which has a density much lower, at least 1/3 of the glass, which have a coefficient of thermal expansion much lower than glass, and you have a performance properties which are very comparable to a glass material. So that unique discovery gave us another quantum leap in the manufacturing of electronics and electrical materials with this particular product. Henceforth, we designed 3 different concepts. One is we want to go to the development of organic light emitting device, and we want to make everything green. Then we want to go to the energy devices like supercapacitor, fuel cells, and the battery, and where we'll be using more of these carbon materials. And the third sector is the use of these materials in the energy devices. So this particular slide will show you how we have demonstrated that particular material, the thin paper, as an effective way to functionalize and then introduce the functionality that we need to manufacture a flexible device, which is in this case a organic light emitting device. Now, what we did, the fundamental, I think, understanding of this material was very important. So we introduced molecular dynamic modeling and DFT at the same time to understand how regioselective this chemistry leads to the functionalization of this cellulosic material in the nano or in atomic level. Once we understood that thing, we could selectively block primary or secondary hydroxyl and can bring different functionality. And this gave us a tremendous fundamental advantage in order for us to make a product which is durable in nature. This particular slide shows how we demonstrated that a cellulosic material, which practically impossible to be stable at a temperature of 100 degrees Celsius for a few hours, we were capable to stabilize it at 195 degrees Celsius for a continuous of 5 hours. And the reason we could do it, because we understood the fundamental stoichiometry of the molecular orientation and their organization, and then selectively functionalize them. So that itself became a very, very, I would say, the transformative results in the area of nanobiotechnology. Second challenge is when you have a substrate which is glass-like, that's not enough. We'll be using, electrodes in that. So we need an anode, you need a barrier to protect between anode and cathode, and then you need a cathode material. And then you need for the OLED also a emissive material. Now, most of the material we found at that time, when you are developing these, are made from either from inorganic materials or from synthetic materials. Our goal was to figure out whether each one of these components can be made from these organic molecules and can be introduced into the system. So one of the platform chemistry we introduced at that time was a green carbon quantum dot for flexible organic devices. And this particular slide will give you a sketch how we have done that. And we demonstrated that if you can articulate the organic molecule to start with, and then you tune that carbonization process by chemical and thermal media system, we can make an effective carbon dots, which has a good quantum yield, at the same time, a good optical and the color behavior or the fluorescence properties. So this particular breakthrough allowed us to use this for OLED or organic light emitting device manufacturing process. So this is our concept, proof of concept of the OLED. So once we have our fundamentals clear, we said, okay, let's try to develop it. And believe it or not, it was made in 2008. And I can guarantee, although we did not publish that paper at that point of time, that blue light you see here, this blue light was not possible to stabilize at that point anywhere, any laboratory in the world. But we did not publish it, we keep it because we wanted to see the durability of this process. So I will run this through just to show you. And this has been developed in 2008. It's a flexible light emitting device. You can see the University of Toronto CBBP and the symbol, right? And this has 5 different layers, and each of those layers are organic, and the whole material is made from a renewable content. So this gives us a confidence that how these biomaterials, with the aids of creativity, science, and engineering principles adoption, can get to a point of commercialization. Now, I'm not going to go to detail. Again, the whole idea here, if you understand the material in the atomic level to the molecular level and then the macro level, we should be able to come to a pragmatic solution to put it in the marketplace. And we, again and again, have demonstrated that this is feasible, and therefore there is nothing it can prevent us from a fundamental research to go to the commercialization process. Okay. So our next chapter, as I said, we started with OLED, but that was the beginning of our game. So we quickly changed. We realized that now we can make this nano entity in large quantity and a reasonably low price. So the next one is that can we not carbonize it and make it carbon? If we can make it carbon, then we can make carbon in the nano level to the macro level to the micro level. And therefore, we can actually change the hierarchical structure of mesopore, micropore, just by tuning their process of carbonization. So we introduced, again, a concept of renewable to carbon energy material. It was 2011. It was the NSERC and ORF-RE project, that is Ontario Research Fund project. Again, it was about total about $12 million project. So what we did there, we did controlled hydrothermal catalytic and thermal carbonization of those entities, which we thought would be a powerful signal for our next generation of carbon materials. We started that, and we brought to a point that which is marketable. One of the key findings in this carbonization process for us was in the early breakthrough, where we found out that by catalytic process, we can carbonize any biomass material, whether it is in nano level, macro level, or micro level, to a single crystal graphite extraction. And this is not something trivial. When I'm talking about single crystal graphite structure, you can make a graphene, right? You can keep on bidding graphites, and at some point in time, it becomes graphene. We didn't have to do that, actually. So what we did in this case, we took the biomass and we selectively catalyze it at a certain temperature. Sometimes it is a hybridization of hydrothermal catalytic and thermal carbonization, and we were able to make a product which are single crystals and which could be functional and also performant. So I'll give you some example. As a result of that discovery, today we were able to make a significant headway in terms of carbon energy sustainability. This is our recent research project, ongoing project, where we put maximum resources from our group to advance this area. The reason we do that, we believe that this renewable nano layer, and even in the graphene layer, carbon can be functionalized. And if they can be functionalized, they can be performant, and they can be useful for many, many applications. This particular slide will give you a holistic idea what we have done so far, and I will give you some example going forward. So defining renewable carbon, it means that you get a biomass, you control your pyrolysis by catalytic mean, by chemical mean, by combination of catalytic, chemical, and thermal means, and then come up with a structure which is simply like graphene type of structure, with some functionality. Functionality such as oxygen, nitrogen. You need that because those tiny amount of other elements like oxygen, nitrogen, phosphorus will help you to further functionalize this material and get into other functional family materials. And that's where we wanted to always see how we can keep tiny amount of these elements so that we can further functionalize it in order for us to get to tune properties of the material. So I'll quickly go through these slides, and I'll quickly show some of the examples of how we did it. So one of the work we have done with Kathy in chemical engineering, because we didn't have a lot of experts in our area in the selective catalysis process. And at that point of time, we developed a simple catalytic chemistry with our hydrothermal and thermal process. And we use sawdust, we use nanofibers, we use lignin, different classes of renewable materials. And what we found that each of these materials can form unique functionality in the carbon. And in this case, I show you, we took black spruce, sawdust. It is from the sawdust mill, and we carbonized it catalytically. And we found at the end of the day, when you get the material, the carbonized material, it shows significant amount of conductive property. And this is, again, primarily given to the formation of single crystal graphite structure. We can see at the moment that means that interlayer distance between two bindings is about 3.2 Angstrom. That means it is about one single crystal graphite structure. So that's type of structure when it develops, your electron mobility or either about ion mobility of this type of material become very, very easy. And that leads to different type of other functional properties. So this particular product actually led to a fundamental breakthrough again in defining the broader sense of renewable materials in the graphene and graphite type of materials. And you can see that here we demonstrated how unique are these. These are the 9-layer boundaries where we just catalyze 300 degrees Celsius under catalytic conditions, and we can make this kind of graphitic structure very easily, which can then give us substantial advantage in terms of their surface area, in terms of the electron transferability, in terms of mesopore and micropore control system, and which will effectively then can be useful for designing fuel cells, supercapacitors, battery, and others. And the next few slides, I wanted to show you the structural differences. Now, when you're talking about the energy material, and particularly graphite type of energy material, one of the important thing is the distribution of its pore structure. Now, what we found that if we take a spruce vis-a-vis a bamboo, we can get a significantly different feature. For example, this is the case where I'm showing the pores of a bamboo. Now, when you take a bamboo has a very unique property. You know, it can draw the water from the core and keep that water fundamentally for a couple of months without being evaporation. Now, we found out that these bamboos are actually forming nanomembranes, and which is very, very similar to that actually used for fuel cell PEM. And we try to understand the mechanism, how Mother Nature developed that membrane in the bamboo. And what we found unique is that when they are developing this cellulosic chain, they are cross-plying it. That means one going in the perpendicular direction, next layer coming in the horizontal direction. So it's like a weaving system. So when we understood that, we take that concept, we actually carbonized bamboo and took the structure out and try to keep or protect that structure in situ in the system. And we were able to do that. And as a result, we were able to keep some of those membrane property. And that leads to our next generation of new Carbonyl structural material and its development. This slide shows that when you have this Carbonyl material in different forms, you can then custom design them and then tune them to the functionalization process so that you can have this uniqueness you need for each and every energy product you are looking for. So one of our primary criteria was make it flexible. Suppose I want to make a flexible battery. So what do we do in that case? we take this product, whether it is nanocellulose or lignin, we electrospin into nanofiber, or we can produce nanofiber, and then we build a sacrificial structure. That means we put it in a form, we freeze dry it, and once we freeze dry it, it is solid, and then we carbonize it. Once we carbonize it, it forms mesopore and micropore. Now, this mesopore and micropore can be then doped with different material, including carbon dots. And as a result, you can see that how mesopore and micropore development and introduction of new doping material can bring different functionality and therefore effectively change the whole paradigm of the energy material industry. So I will show you two simple examples which are published recently. Ice templating process. So we took nanocellulose, as I said, it was pretty cheap for us to do that. What we did, we put it in liquid nitrogen, we mixed with lignin, so that lignin can be embedded with nanocellulose, and then we freeze it in the liquid nitrogen. Once we did it, we dry it in a freeze drying process, then undergone carbonization. And after carbonization, what we found that this, and you can see at the bottom, right? These are the two structures, before carbonization, after carbonization. The carbonization process gives very unique mesopore structure, which is about 10, 15 nanometers. And this allowed us to actually help to control the electron permeability in the system. The electron transition will very much depends on the pore size. Now, if you have to, say in a battery system, you have to, if you are in a separator system, you want to delay your ionic mobility. By controlling this nanopores or the mesopore, you are able to actually delay that process. And therefore, when you need the electron transfer to be faster, you can do that. And when you need to delay it, you can control it by mesopore structure control. And this leads to solid state battery as an example. So you can have a solid state battery with a separator, which is actually mesoporous in nature as the control porosity, and therefore you can control the ionic mobility. And then your anode material is self-generating with lithium, and as it generates the power. Lithium ion transfers back to the cathode, and as a result, you get a very compact solid state battery concept. So this particular work actually led to that kind of product development in the future. So this is an example where we have demonstrated the use of this material in the battery development. So we said that lignin carbon aerogel, carbon dot, or the graphene dot for energy device and BAV electronics material. So again, we made this carbon aerogel. It's a product from nanocellulose and lignin with a carbonized one. Then we did graphene quantum dot. We impregnated or doped into it. We got into GUK decorated carbon aerogels, and we found this particular aerogel can be a cathode, can be an anode material, it can be a separator material, depending on how we change their pore structure and their layers. And we demonstrated in this particular one, this has been published, that you can actually make a bio battery. That means each and every component you can get from natural resource. You don't need, except lithium, some of the inorganics and the metals, which will cross path between anode and cathode. Most of the products can be actually made from this carbonaceous material. And this is, we define it as a bio battery or bio capacitor, bio cell, biofuel cells product. So these are some of the detail. I don't want to go to the detail because of the time. So it's a fine chemistry combined with fundamental understanding of the physics, and then using engineering principle to put it in a form so that it can be mass produced. So these are the three concepts we always introduce when we grow our research. These are some of the examples. If you don't believe that it can happen, this is an example. See that? So what we actually try to prove from our PhD students who follow through our PDF, we give the talks, fundamental talks to our PhD student. Our PDF has the responsibility to make a device, and that device should demonstrate what actually current to the system. So in this case, we made actually 4 or 5 devices, and we demonstrated that actually we can achieve almost the same feature that is actually done by the other companies like graphites and other things of conventional other electron what do you call capacitor system. And there are some other examples. These are actually for other energy devices, but overall, I can tell you that this type of trivial research, so-called, can really be fine-tuned and transformed into practice. And this is where I think the engineering science come into play. And therefore, having the solid context of the engineering science, we were able to demonstrate that all these materials in the proof of concept level is possible to work and develop this kind of technology. Further going forward, what we wanted to do, not only use this material, but also we wanted to transform their manufacturing process. So we said, okay, we have this carbon material, we have lignin, and we know polymer a little bit because we are polymer scientists. Basically, our group, mostly they have their polymer background. So we said that, well, if we have to make a battery cell, can we use this instead of going through the injection process or extrusion process? Can we do it in 3D printing? So one of our actually master students has developed this machine. This is a 3D printer, but with a 3D geometry, or we can say it's a 4D printing process. Why it is 4D? It's a 3D design, but because it is living polymerization mechanism, so we bring a solid state 4 dimensions, and I'll show you how it's happening. So what we are doing is, here we are using tannin and carbon dots as a combined resources of polymer, and then you are using an acid catalyzed system. As it's injecting the process by layer, the one layer is differentiating the other layer. Once as the first layer forms, it starts cross-linking. This cross-linking is a sort of a living polymerization process. So as you build a second layer, third layer, it solidifies. So therefore, there is no need to further cross-linking this process separately as we do in a normal system. So by this way, we demonstrated that we can not only reduce the processing time or the processing steps, but also we can make a product, whether it is a anode, a cathode, or something very similar, in one single 4D geometry system. And we are not able to make it in a scale-up stage right now, but we have been working with a company in Montreal, and we're hoping that in near future, we'll be able to scale up to a level that we can make those electrodes and separators using this technology. Going forward, we are talking about something about the chemistry. Again, with our carbon material, we can functionalize. Because of our solid chemistry understanding of this carbon material, we can selectively functionalize this hydroxyl group or oxygen group in a way that we can clear the property. This is another example where Total, the company who makes a lot of cell gas, they came up with an idea, hey, we are making a lot of ethylene, and the polyethylene will be cheap and polypropylene will be very, very expensive. So why not try to make polyethylene like polypropylene? So one of our PhD students took this project. We said, well, let's see whether we can graphitize a part of this polyethylene and come up with a solution which will be probably very similar to that of the polypropylene structure. Exactly, that's what it happened. So this is the process chemistry. I'm not going to detail. Definitely, I'll be happy to answer questions. But at the end of the day, when you have done this, graphene functionalization with our knowledge of chemistry and the combination of the chemical engineering and mechanical engineering and process engineering, at the end of the day, we came up with a solution. And we demonstrated. I can show you in this slide. Look at this. This is actually polypropylene, and it's a combination of 90% polyethylene and 10% polypropylene, and we blended it. And our goal was to make 90% polyethylene behave like polypropylene, which is very high performance compared to polypropylene in terms of glass transition temperature and HDT. So what we were able to do, we were selectively orient this graphene structure at the interface of the polyethylene and polypropylene. And therefore, we uniquely make a unitransition phase by selectively adding this functional group in the graphene. And hence, the whole polymer brain become a unique one system structure, resulting in a single polymer is a new polymer system. We don't say it's a blend anymore. It's a new polymer which has 90% ethylene structure and 10% propylene structure, but giving the performance of polypropylene. And we achieved that, and we demonstrated that with an example in the car industry. Car industry use a lot of polypropylene. They never use polyethylene because of the low thermal and heat deformation temperature. With this technology, the polyethylene heat deformation temperature from 47, we came up to 68. And which is actually, that's a game changer for the petrochemical industry. And this process is under commercialization still up. So we are working with Total and only hoping in future it could be a cost-effective way to manufacture that product. Another example of where we introduce this in the fuel cell industry, and again the bipolar plates, which were made from a different sort of a graphitic structure. Instead of having those materials synthetic, we introduce our own graphitic material, and we have demonstrated that we are perfectly matching those performance needed by DOE for the fuel cell industry. And again, one of this project is very under very intense research program for the commercialization process. We are not there yet. We'll be doing that. The last phase, the last 5 minutes, I want to devote on our other energy area, which we are working in collaboration with Professor Jeff Oz in the chemistry. One of the early stage in 2015, a group of team came up with some idea that, well, we have to do something with CO2. Well, there's a lot of CO2, and there's a lot of biomaterials existing. So how we can really tag in and combine them together? So one of the concepts at that time, when I was talking to Jeff, we said that Jeff has some catalyst which can probably reduce CO2 to CO at the same time, and that CO can be used for some other applications. So with that concept came in, we launched a project in 2015 with some of the industry folks, and in 2017 we came up with a product where we can capture CO2 from a power station, purify them, and then transform into some of the substance and chemical, and then transform into a product. And this leads to 2017 submission of our X Prize. And this particular project gone to final 10, but it didn't get the final prize. But even then, being final 10, it has a significant draw in our through, because the way we took the project is very different compared to what other took. So in this case, what we did, we captured the carbon in terms of CO2, we purified that, and then use some nanocatalysis technology to convert it into carbonates, particularly carbonate type of material. And then use these carbonates as a base material for making polymer composites and composite materials as a base. So in this particular case, the product came out and resulted in a capture capacity. This is actually a product between Canada-China collaboration. It was done in 2017. And this is a project where you can see that this is me here, and this is one of my partners from University of Toronto. He's a graduate from chemical engineering. We actually developed a carbon capture plant and to demonstrate that from the power station, we can capture it, we can purify it to the level of 99%. Once it happens, our next stage was how we use this material and make some products. This video is not good, but what I wanted to say here, we combine two technologies, our nanocellulose technology and the CO2 technology. So we designed an extruder, which is a reactive mixer where we use hyper low temperature, very low temperature. We freeze actually the fiber material, and then we defibrillate the fiber in situ. This is an extruder, which has been designed by us. And then we started dispersing it in polylactic acid. Polylactic acid is a biodegradable or compostable polymer. So what happened in the first phase of the extrusion process, this polylactic acid and nanocellulose being dispersed, forming a nanocomposite. And then we introduced before the tandem, we introduced CO2 saturation point. So where we have introduced up to 3 to 4% CO2 in the system in order for us to get that saturation level, we can get a porous structure. So you will see down the line that during this is a commercial scale, actually. I'm talking about the commercial scale now. So you see that this particular material coming out is a foamed cellulose nanocomposite, which is 100% biodegradable. And that has never happened before. And here we have a proper combination of supercritical CO2, hyper low temperatures, nanocellulose dispersed in a basic polymer, which is biodegradable, and a foamed material coming out continuously in a sheet form, which can be used for many, many applications. And this is the outcome of our commercial demonstration in a C4X project. Although this project didn't win, but this project got lots of funding, and we do have actually 2 trial facilities, one in here, one in the United States, and there are a lot of other work going on in this area in order for us to put it in the final commercial stage. I will stop it here because I don't think that we want to go further. So I'm just going to go through the few designs. So our latest project is actually changing the dynamics of the diesel fuels. Replace diesel wherever you have with renewable or CO2. So transformative ideas in the catalysis in the lab and elsewhere. So what we believe that if we can make a molecule, which is very simple for us, this is known as dimethyl ether. It's a high energy density liquid graphene fuel. If we can make it, we'll be able to transform some of this industry, like shipping industry and also the trucking industry. And this compares to about fuel cell and hydrogen dogma, right? So we said a carbon neutral fuel with relatively high energy density demonstrated to be an alternative energy carrier for transportation. And we tagged into it. One of our PhD students recently finished, Arthan, has demonstrated that DME chemistry can be done through a methanol transformation route. If we can reduce CO2 to CO, and then to form methanol, methanol can be subsequently transformed into DME, and DME can be then used for different applications. And this paper has been published recently in Nature Catalyst. So this is our game plan. So we make this DME, whether it is one-step process or a two-step through sequence of methanol or direct formation of DME. Either way, it is going to change the energy industry. Why? Because if we have a DME as a liquid fuel, which can be used even for trucks or other type of energy user, but at the same time, if we can use a DME and then we do the reverse catalysis, we can then reform into hydrogen, then we can change the fuel cell industry totally. Because one of the obstacles of the hydrogen economy today is the transportation. Now, if you have to transport hydrogen from place A to place B, it's a lot of effort and the design and safety aspect. So the concept here, if we have a DME, which is available in a station, like in a gas station, and then locally you transform the DME into hydrogen by reforming, then you have an easier way to to use this hydrogen without transportation process. So this project has been conceptualized now. We are working. Arthan has been really spearheading this project, where we are looking at actually LED sources, which is 4 electron sources with a unique structure of the reactor. Here we are looking at the 3D design porous structure, and this porous structure. The main objective having this porous structure is to improve the photon efficiency, how we can improve the use of this LED. In this case, you can see that the processor, and use that to effectively react with the catalyst, which is embedded in the system, and therefore efficiently transform the carbon dioxide to CO2 and via a route and a direct route to DME eventually. So that's the concept we are talking about. And there are some of the related projects going on, where we also found that during this process of DME production, if the catalyst is really unique, we not only make DME, we can make carbon actually. We can make carbon nanotubes or carbon materials, which is an extra addition. These carbon materials can in situ, can react, act as a high surface area, therefore accelerate the process of the DME formation. At the same time, at the end of the day, it can be a byproduct, which then can be used as a material as such for different applications. So therefore, all this will lead to some sort of fine chemistry, at the same time engineering of the reactors, forming this kind of product. This is another student from MIE, joint project from Jeff Ozin and myself, where we are looking at different ways of configuring catalyst and putting in the concept of a reactor, and then trying to find out how we can optimize this production of CO2, so CO2 to CO, and then effectively use it to convert into a DME system, eventually formation of hydrogen as well. So this yes. So
sorry,
this is,
can I just?
Yeah, go ahead.
Can I just interrupt? I wanted to say we're a few minutes past 1. I know we've had a few people drop off, and I do apologize for interrupting, but I just want to say that and you know, I think we can hang around for a few more minutes. You may want to just finish up here.
Actually, I'm mostly done, you know. So this is my last.
Okay.
All right. So this is our hydrogen production system process. So this concept we introduced, and we were working on that, how to get this hydrogen easily not transporting, but by easily available in the gas station with these renewable contents, which are introduced with the formation of the reaction chemistry, reactor design, at the same time catalytic chemistry. With that note, I want to send it, and thank you for it. I know that I didn't have time with me, that's why.
Well, you know what? Listen, it's always delightful listening to you, because I have the feeling you could tell us much more. To those of you who are still with us, I really appreciate it, and I wonder. We had some other plans, I think, for Mohini just for the next little while, but I think what would be easiest would